You are watching AI Paperslop, and today we are looking at energy-guided flow matching by Haiyang Tang and team. So standard flow matching for pixel space generation, it kind of struggles because it forces the model to learn global structure and high-frequency details simultaneously.
Right, it's aiming at a fixed clean image endpoint.
Exactly. But this paper fixes that bottleneck by introducing energy-guided flow matching, or EGFM. It uses a moving spectral endpoint, explicitly modeling a coarse-to-fine trajectory. So it smoothly transitions from this heavily low-pass, blurry image to the full-resolution target.
And it does this adaptively.
Yeah, that's the kicker. It is customized to the spectral energy of each specific image. The result is, well, up to 4 times faster training on architectures like Pixel.XL, 0 inference overhead, and an impressive 1.45 FID on ImageNet 256 by 256.
Yeah, that is a incredibly dense summary, but perfectly accurate. And to truly appreciate what Haiyang Tang and this team from Kish and JD.com have pulled off, we kind of need to unpack why this intervention was so desperately needed in the first place.
Yeah, let's slow down just a bit to ground everyone.
Right, because if you are an ML engineer working on these models, you know firsthand the current bottleneck of pixel space generative modeling.
I mean, pixel space generation has been this massive focus lately, specifically because it avoids the lossy latent compression of latent diffusion models, right? Like, if you are building a latent diffusion model, you rely on a VAE.
Variational autoencoder, exactly.
Yeah, and by its very nature, a VAE discards high-frequency details just to compress the image into a smaller latent space. Pixel space modeling, it skips that entirely. You operate on the raw pixels, so you keep all those really fine-grained details.
Exactly. It preserves the absolute fidelity of the image because you are generating directly in the high-dimensional space. But, that high dimensionality introduces a massive optimization headache.
Oh, for sure.
Because in standard flow matching, the math essentially connects a noise distribution directly to a fixed clean image endpoint. You establish a floaty path that just interpolates from pure Gaussian noise directly toward that perfect full spectrum clean image.
Let me break down what that actually means for the neural network during training, because I think that's the core of the problem here. If you think about what an image actually is, it's really just a combination of spatial frequencies.
Right, low and high.
Yeah, you have the low frequency components, which give you the broad global structure, like the overall layout of shapes, the big blocks of color. And then you have high frequency components, which are your sharp edges, the fine textures.
Granular detail.
Exactly, like the pores on a face or the leaves on a tree. It's like trying to sculpt a statue by simultaneously carving the rough silhouette and the delicate eyelashes.
Oh, that's a great analogy.
Right, it's just an impossible cognitive load for the network. Shouldn't we be explicitly teaching the model to work coarse-to-fine?
Precisely. Because if a model is aiming at a fixed endpoint throughout the entire generation process, the temporal emergence of these different spatial frequencies is left, well, completely up to the network to figure out implicitly. The loss function is basically just telling it, predict this final crisp image right from time step 0.
So the model basically has to guess the order of operations. It has to implicitly figure out that it should probably build the global structure first before adding the high-frequency textures.
Yeah, but nothing in the math is actually guiding it to do that. Unified modeling on full frequencies all at once just increases the difficulty of task learning exponentially.
Which means you just have to throw brute force at it, right?
Exactly. To brute force a solution where the model figures out this complex frequency evolution on its own, it requires massive model capacity and hundreds upon hundreds of training epochs. And that is the exact intuition driving this paper.
Right. So instead of trying to fix this with, I don't know, architectural hacks or auxiliary losses, they look at the fundamental flaw in the trajectory itself.
Yeah, they realize a path that explicitly integrates the frequency evolution of images would provide the perfect inductive bias. The model could securely establish the global structure before it ever has to worry about synthesizing high-frequency details.
Which brings us back to the statue analogy. Since fixed endpoints force this carve the eyelashes and silhouette at the same time problem, the authors just decided to fix the target itself.
But they had to do it without breaking the underlying math.
Right. The flow matching math relies on very strict boundary distributions. So enter the moving spectral endpoint. How does this actually work in EGFM?
So they denote this moving target as y sub t of x. And instead of pointing the velocity of the flow matching model at the fixed clean image X at every single time step, they replace it with this Heat-Kernel filtered endpoint.
Okay, so what does that look like at the start of generation?
Well, at time step t equals 0, the endpoint is a heavily low-pass filtered version of the image.
So if you're trying to visualize this right now, imagine at t equals 0, you are trying to generate a picture of an owl perched on a branch. The target the network is aiming at isn't a crisp owl.
No, not at all.
It's just this blurry, blobby representation of the brown and green colors and the rough shapes. All the high frequencies, like the individual feathers or the bark texture, they're completely stripped out.
Exactly. And then, as time progresses from 0 to 1, those high-frequency signals are progressively released back into the target. The target image gradually sharpens.
Until it hits the final image.
Right. By the time you reach equals 1, the endpoint has become the full spectrum, perfectly clean image. And what's fascinating here is how they achieve this mathematically using that Heat-Kernel response formula.
Yeah, let's get into the mechanics of that formula a bit, because I know the technical listeners really want to know how the network interacts with this.
Sure. So the Heat-Kernel response is used to build a nested family of low-pass images. They operate entirely in the frequency domain using Fourier transforms. Conceptually, they define a normalized radial frequency and apply, well, it's essentially a Gaussian-like decay based on a variable they call heat time.
Okay, and how does heat time control the frequencies?
When heat time is high, which corresponds to the very beginning of the generation process, the high frequencies are heavily attenuated. Then, as heat time decreases toward 0, those higher frequencies are allowed back into the signal.
But this preserves the core math of flow matching, right? Because I feel like that's the part that really stood out to me as so clever.
It's arguably the most elegant mathematical maneuver in the entire paper. In flow matching, your boundary conditions are basically sacred. The start must be pure noise, and the end must be the true data distribution.
Right, so you can't just mess with the endpoints without breaking the whole framework.
Exactly. But because the interpolation at t equals 0 still heavily weights the Gaussian noise, z sub 0 remains pure Gaussian noise. And because at t equals 1, the target is defined to perfectly equal the clean image, z sub 1 is still the clean image.
So they preserve all the boundary constraints perfectly.
Yeah, they haven't broken the framework at all. They have just completely altered the trajectory the model takes to get there.
I have to play devil's advocate here, though, or at least ask a clarifying question about the loss function.
Sure, go for it.
If the target is moving during the training process, how does the model actually learn to hit it? I mean, isn't that like a driving instructor constantly moving the traffic cones while you're trying to parallel park?
That's a really fun way to picture it.
I just feel like the network would get completely unstable trying to chase a moving target, you know?
It's a great analogy, but let's reframe how those cones are moving. If the driving instructor was moving the cones arbitrarily, then yeah, it would be impossible, and the loss would just explode.
Right.
But what if the cones were actually being moved from a very easy, wide, forgiving path into the exact, narrow, final parking spot, and they are moving in a mathematically predictable way?
Oh, I see. So the early steps are just inherently easier to predict.
Exactly. At the beginning of the trajectory, the low-pass manifold is structurally much simpler to hit. The model isn't being tricked by the moving cones, it's being guided by them.
So how does the velocity field account for that movement in the math?
This is the crucial part of the how. The velocity vector that the neural network is trying to predict isn't just pointing toward the current moving endpoint.
What else is it pointing at?
It is trained to point toward the endpoint, plus a term that calculates the exact derivative, the actual motion, of the endpoint itself.
Wait, really? It factors in the velocity of the target.
Yes. Because they define the endpoint using a differentiable Heat-Kernel function, they can calculate exactly how fast and in what direction the endpoint is moving at any given time step. It's a highly structured, coarse-to-fine curved path that is actually vastly easier for the neural network to follow than a straight line to a highly complex target.
Okay, that makes a lot of sense. You're basically building the scaffolding before you put up the drywall, and the math tells the network exactly how fast the scaffolding is coming down.
Perfect way to put it.
But moving the endpoint is only half the battle, right? Because if you applied a universal blur-to-sharp schedule for every single image in your data set, the system would break down.
It would absolutely fail.
Right, because a smooth blue sky doesn't need the same scaffolding as a dense forest. So how do they account for that variance?
And this is where the paper elevates from a very good theoretical idea to just a phenomenal piece of applied engineering. They introduce the concept of sample adaptive heat time, denoted as h of x.
Sample adaptive, so it changes per image.
Yes, this is the variable that governs the release rate of the frequencies. And crucial to their success, it is calculated uniquely for every single image.
To give you all a visual from the paper, they compare two very different images to explain this. Sample A is a picture of a rough, highly textured mat with a metal lock sitting on it.
Right.
And sample B is a smooth, kind of out-of-focus baseball.
And if you look at the spectral composition of those two images, they are fundamentally different. Sample A, that textured mat, has a massive amount of its information locked up in the high-frequency bands.
Like the intricate weave of the mat.
Exactly. The sharp edges of the lock, the weave, that is all high-frequency data. But sample B, the baseball, is mostly low-frequency. The smooth white leather, the soft blurred background.
Basically, just the red stitching occupies the higher frequencies.
Right, so you simply cannot treat them the same way during training. If you used a fixed schedule at time step t equals 0.5, you might have released all the necessary information for the baseball, but the textured mat would still be desperately missing its core identifying features.
So the textured mat needs its high frequencies way earlier.
Exactly. The authors ensure that sample A requires a much faster decrease in heat time than sample B, just to properly release its complex high frequencies early enough in the generation process.
Let me see if I have the math right on how they adapt this on the fly, because this is where Parseval's theorem comes in, right?
Yes, it does.
And Parseval's theorem is beautiful because it essentially proves energy conservation. Like, the total energy of the image in the spatial pixel space is exactly equal to the total energy in the frequency wave space.
That's right.
So they take the L2 distance, the physical gap between the blurry image and the clean image in pixel space, but they map it into the frequency domain to measure the missing spectral energy. Is that accurate?
That is a flawless breakdown. They take the initial low-pass endpoint, which is the absolute blurriest version of the image at t equals 0, and they calculate the L2 distance to the perfectly clean image.
So they know exactly what's missing right from the start.
Exactly. By using Parseval's theorem, it tells the algorithm exactly how much high-frequency energy is currently missing from the target. They then build a schedule that guarantees a linear release of that specific energy over time.
So instead of standardizing the clock, they are standardizing the progress. I love this.
It's remarkably intuitive when you break it down.
It really is. It's like a chef knowing exactly how much salt to add to a dish by constantly tasting the broth, rather than just blindly adding 1 teaspoon every 5 minutes, regardless of whether they are cooking a delicate soup or a heavy stew.
I like that.
A step at t equals 0.5 means exactly 50% of the spectral energy has been recovered, regardless of whether it's a picture of a complex forest or a smooth blue sky.
That is the perfect way to phrase it. They align the shared time variable to reflect comparable relative progress across completely divergent samples. It yields a coarse-to-fine evolution that is matched perfectly to the intrinsic content of every single image in the dataset.
Okay, but if you're an ML engineer listening right now, alarm bells are probably going off in your head about compute costs.
Oh, absolutely.
Because calculating sample-specific spectral gaps via Fourier transforms, dynamically adjusting heat time, I mean, that sounds incredibly computationally expensive.
It does sound heavy.
Right. If you are doing this for every single image, at every single step, in a data set of millions of images, doesn't your wall clock time just completely tank? We have to address the engineering reality here.
It is the most natural question to ask, and it's where the authors provide a very satisfying answer. The computational overhead is actually negligible.
Okay, define negligible. Because negligible to a researcher with a massive compute cluster is very different from negligible to a tiny startup.
Fair point. But they measured this meticulously. The extra math required to compute the moving target, the spectral gap, and the endpoint motion term, it adds at most between a 0.41% to 4.81% wall clock time per step.
Wait, really? Under 5%?
Yeah. They tested this across major architectures like DiCO-XL and various sizes of pixel bead. The largest measured increase in per-sample compute specifically for target construction was only 0.0256%.
Wow, so less than a 5% hit on training speed in the absolute worst-case scenario. How did they keep it that low with all those Fourier transforms?
Because a lot of this can be pre-computed or efficiently batched. The spectral gap calculation and the scheduling, they're mathematically deterministic based on the clean image, so you aren't running heavy neural network passes to figure it out.
Oh, it's just matrix math.
Exactly, which GPUs are extraordinarily good at.
And that's just the training side. It gets even better because the inference overhead is exactly 0.
Yes, 0.
Explain that for me. How is it possible to have 0 overhead during inference if the generative trajectory is completely different from standard flow matching?
Because EGFM requires absolutely 0 architectural changes to the backbone.
Ah, I see.
During inference, you are not constructing a target anymore. You are just evaluating the learned velocity field. You don't run any filtering, you don't run any fast Fourier transforms, you don't compute spectral energy.
You just run the standard samplers.
Precisely. You just start with noise and use the standard differential equation solvers, like the 50-step Hume sampler or the 100-step flow DPM solver, just exactly as you would with standard flow matching. You are simply traversing a fundamentally better trained velocity field.
So we're talking about a practically free lunch in terms of inference compute.
Pretty much.
Let's talk about the training efficiency gains then, because if the overhead is that low, the speed up must be massive to justify the implementation in the first place.
It is massive. Because the model isn't wasting hundreds of millions of parameters and countless epochs just trying to implicitly figure out the frequency curriculum, it learns up to 4 times faster.
4 times?
Yeah, look at Pixel DTXL. With standard flow matching, it takes 800 epochs to reach an FID of 1.54. But with energy-guided flow matching, it hits a 1.55 FID in just 200 epochs.
4 times the efficiency. That is hundreds of GPU hours saved. I mean, for AI researchers, that fundamentally changes how quickly you can iterate on ideas.
It really does.
But wait, I have another pushback here. If we radically alter the probability path and the velocity targets the way EGFM does, essentially bending the trajectory from a straight line into a curve, standard classifier free guidance, or CFG, scales must completely break right.
If we connect this to the bigger picture of diffusion and flow matching, you are entirely correct to point that out. CFG relies on the geometric relationship between the conditioned and unconditioned velocity predictions.
Because you're essentially extrapolating a vector in a high-dimensional space.
Right. And by bending the trajectory into a sample-adaptive curve, that geometry shifts. The vectors just don't behave the same way they do on a straight-line interpolation. The authors fully acknowledged this and had to systematically retune it.
So what did they find when they mapped out the new geometry?
They found a very strict U-shaped curve for the CFG scale. When they tested it on ImageNet, an unguided model gave an FID of 11.60. But as they increased the scale, it dropped beautifully, hitting the absolute minimum, a stellar FID of 1.45, at a CFG scale of exactly 2.55.
And if they pushed it higher?
If they pushed it to, say, a scale of 4.0, the FID started to degrade again up to 1.70. This is significantly different from the optimal scales usually found in standard flow matching, which proves that the trajectory modification fundamentally changes the dynamics of guidance.
So with the theory sound, the compute costs practically non-existent, and the guidance mathematically tuned. Let's look at the actual benchmark scoreboards.
Right.
Does this state-of-the-art theory translate to state-of-the-art results?
Unquestionably. On the ImageNet 256 by 256 benchmark, which is highly competitive, EGFM reaches that phenomenal FID of 1.45 at 600 epochs.
And for context for you listening, an FID, or fresh inception distance, of 1.45 means the generated images are practically indistinguishable from the real dataset in terms of distribution. It is an incredibly low score.
It really is.
And that's class-conditional image generation, right?
Yes. And when they pushed the resolution to 512 by 512, they achieved an FID of 1.58. But what is truly remarkable there is they achieved it with only 40 high-resolution adaptation epochs.
40 epochs to adapt to double the resolution.
Plus 40.
That speaks volumes about how structurally robust the representations are that the model learns early on. I mean, if it understands the low-frequency global structure perfectly, scaling the resolution is just a matter of refining the highest frequencies.
Exactly.
It already knows where the shapes are, just needs to paint in the extra pixels, which the energy-guided trajectory handles beautifully.
The foundational scaffold is rock solid. And they didn't stop at class-conditional generation either. They transferred EGFM to text-to-image generation at 512.2 by 512 resolution just to see if it generalized.
And did it.
The results there were equally impressive. They hit a score of 0.85 on GenEval and 83.9 on DPG-Bench.
And they did all of this without changing the backbones at all.
That is the most crucial takeaway for practitioners here. These gains were proven across multiple distinct architectures, both Deco and pixel deep.
So no weird architectural tricks.
None. They didn't need to add new auxiliary losses to the training pipeline. They didn't need complex hacks like hourglass attention or hierarchical global local structures. The underlying model remained entirely vanilla.
So what does this all mean for the field moving forward?
It proves, definitively, that how you parameterize the generative trajectory is just as important as how many parameters you pack into the model itself.
We've been so obsessed with scaling up.
Right. Exactly. Bigger transformers, larger data sets, heavier compute clusters. We sometimes just completely overlook the mathematical path we are asking these models to walk. Energy-guided flow matching shows that a smarter, sample-adaptive path can effectively multiply your model's capability without adding a single weight.
It's a triumph of algorithmic elegance over pure brute force. You aren't just giving the model a massive engine, you're actually giving it a map that makes sense.
Which brings us to a fascinating implication, I think. If aligning the generative trajectory to the intrinsic spectral energy of an image drastically improves learning, this raises an important question. How could this be applied to non-visual modalities?
Oh, wow. That is a huge thought. Because how do you measure frequency in something that isn't a picture?
Well, think about it. Language models generate token distributions. Could we design a sample-adaptive, energy-guided flow matching for text?
Like what constitutes the low-frequency global structure of a paragraph?
Exactly. Maybe it's the grammatical syntax or the broad topic versus the high-frequency specific, rare vocabulary choices.
That makes total sense.
Or consider embodied robotics. Could we map the continuous action spaces of a robot into a similar energy domain, guiding a robot to learn the broad, gross motor movements of a task before it refines the delicate, high-frequency, fine motor skills?
Standardizing the progress of generation, regardless of the data type, that is a massive paradigm shift to ponder. It actually makes you wonder about biological learning, too, you know?
Absolutely.
Because human infants are born extremely nearsighted, seeing only blurry, low-frequency shapes. Their vision naturally sharpens over months as their brains develop and process more complex inputs. Maybe evolution discovered energy-guided flow matching millions of years ago, and we are just now writing down the math for it in neural networks.
It's a beautiful way to frame it.
It takes us right back to the beginning. Instead of forcing the network to carve the statue and the eyelashes at exactly the same time, we give it the tools to understand what a silhouette even is and let it naturally refine from there. Well, that wraps up this exploration. Thank you for joining us on this episode of AI Paper Slop. Keep questioning the algorithms, and we will see you next time.